Is this? Oh, okay. This is not a message. This is just a transcript. Okay. Um, okay, great. Yes, Chaitanya, this question will be answered in this course. We touched upon a little bit about how chemistry, computational chemistry will help you in your academic career and journey in chemistry. We can talk a little bit more about it, and actually we can also do a 1 hour session instead of doing a. Yeah, we can also touch on that. But let's get back to what we were working on so that we don't lose track. So we had the paper, we have the Morse function. So we were looking at that. Let's open the hyperlink. Okay. I hope you can see the artifact. So what we did is we said that the interaction between the interaction that entails a bond, essentially, can be described by a quadratic potential. So it can be a spring or it can be a Morse potential, which essentially means it's a spring that's not an ideal spring that can elongate and also lead to a dissociation. Which is what also typically happens if you know, as a kid or even now, if you take a spring and you really stretch it out, it becomes flat. Um, that's how real springs behave. So, and we saw that we can tune the parameters to affect the depth of this potential, affect the width, and also where the equilibrium distance is. So this is to give you some idea about or some intuition about what the bond dissociation would look like. So this is here is this your equilibrium bond distance. If you go a little bit up, the system will start to vibrate because it has some additional energy now. And if you vibrate it too much, or if you take it too really like apart, then it will break. So this is what we were doing. So we looked into the how to encode bonded interactions. We also looked into how the model encodes the equilibrium bond distance. It is done in terms of the bond radius of the atoms, but also looks into bond order and the electronegativity to actually construct this construct these parameters. Okay, moving on. You also need force constant. So if you're trying to model something with a spring or like with any kind of potential, you also need to sort of tune the strength of your interaction. And without going into detail, they have made some certain models followed something called the Badger rules about the bounding curve, did some mathematical tricks, and here and there they eventually came across what this force constant would look like. And this force constant, if you remember from how a spring and mass system work, this describes how your system will vibrate. So if you put the system out of equilibrium, it will not, let's stay static, it will vibrate. And in fact, from quantum mechanics, if you have studied a bit of the hydrogen atom, you would know that even if you don't put additional energy in the system, even a 0 Kelvin system has some 0 point energy, which leads to a certain vibrational mode. That's not a part that we'll touch upon in this course, but just for you to know. And if you look at the overall expression, it is something that relates to the atomic numbers and the distance, but this essentially relates to the equilibrium distance that you have. So this is some sort of you can think of it more of a dipole like term. If you have done the derivation of the classical dipole moments, you might recognize this cubic term that arises from a distribution of charges. But not to dwell a lot on it, you get an idea that how you construct a potential. Similarly, you can do angular distortion. So instead of using a harmonic potential here, they use a cosine function. If you know, the cosine function also oscillates, and if you are at the minimum of the cosine function, you can sort of like, it's kind of similar to being in a parabola, but not exactly because it's periodic and it does not go to infinity. But you can model it, and then again you need some kind of force constant that is now dependent on three. It's a three-body term. So this Ij in the bond stretching, it was a two-body term, which means it was dependent on two atoms. Now it's a three-body term dependent on three atoms, so it gets a little bit more, slightly more complicated. There are more mathematical tricks that go here and there. But what I want to sort of bring your attention to is that they also use some sort of natural angles as the standard bond angles. So if you start with O3, which means it's oxygen that is in a tetrahedral state, it will fix the angle to be close to that of water. But for tetrahedral sulfur, it will go to 92 degrees, which is derived from the H2S, and they also have certain exceptions. So this generally gives you good quality angles. So your starting structure is good within this or your guess of the structure is good. If you look at once they have done that, then they also implement the torsion force, the potential to model the torsion. And I told you I'll give you some intuition there. So delivering on that promise, let's look at another artifact. So I will open it for you, but please feel free to also scan it, open it on your mobile device. But don't start checking your WhatsApp or something else, otherwise you will get distracted. So this is the representation of the torsion function, and I'll tell you what it means. Let's say you have two sp3 hybridized centers, right? So this is what your model would look like. So these are three atoms, and when you change the angle, so maybe I can fit it to one screen. It's a little bit, yeah. So if you change the torsion angle, see how the thing is rotating. See, so essentially you make a plane of these three atoms, and the fourth atom is actually rotating. So that's the change in the torsional angle. There are different ways to represent this. You can also have two atoms moving to represent the relative motion, but this is just a way to give you an idea of how a four body potential looks like, how the dihedral angle or the torsion angle can change. And this is very important. If you have read a little bit of biochemistry, you might have gone into Ramachandran plots and stuff. You know that this sort of angles, these dihedral rotation angles, are really important to model the interactions in proteins. So, and you see how so if you are here, then this is a stable structure because now you have, like, the energy is minimized. But if you rotate it further, it will go up. If you rotate it back, it goes up and down and up. And what you can imagine is that if you give this system a certain amount of energy, which means, let's say you heat up the system and the system starts to move around, the bonds will change. Then if the energy that it gains from heat is enough to sort of, like, so let's say if it's in minima now, if it's enough to drive it over the hill, it will sample another structure. And that's how molecules vibrate and move around. Let me get this person in. Okay, so let's get back to the screen. So this gives you some intuition about the torsion, the force that we are the kind of interaction that we are looking into. So this is not there's no chat here. Okay. And if you have a question, if you put it in the chat, it will be difficult for me to see it. I don't have a moderator now. So please just raise your hand or unmute your mic and speak. So is this clear for everyone? Do you get a good intuition for what a torsion potential looks like, what the torsion angle looks like?
Yes, sir.
I assume it's clear in the chat. Then I go back to the safety of PowerPoint. Okay. So now you have learned about, you learned a little bit about what the interaction looks like in a Hamiltonian. We did not talk about kinetic energy because it's kind of trivial. If the molecules move, half mv square gives you the kinetic energy, or p square by 2m gives you the kinetic energy. It's important to understand, and this you might remember from when you were reading about kinetic theory of gases. Or you might not also remember. It's not a very memorable thing, to be honest. But if you have a system of particles and you put it at a certain temperature, this is a statistical. You describe it as a statistical phenomenon. What that means is that you will have a range of velocities that the system can sample, and this is very important in molecular dynamics simulations. So if you have a system that is equilibrated at a certain temperature, there is a range of velocities that it can have. If you don't have temperature, then you don't have to worry too much about it. But just to keep that in mind, that when you apply a temperature, there is a range of energies that the system can sample, which can give rise to interesting kind of dynamics because it can have different kinds of velocities. Now let's look into what happens when we want to optimize the geometry of a system. So if you remember, and maybe if you don't, I'll show you this movie again. And by the way, I'm not in full screen. Is this still good, like visible well to all of you, or are you having trouble seeing it?
So all fine.
All fine. Okay, good to know that. Yeah, thanks. So, I showed you this video. Maybe I'll accelerate it a bit. And what I said is, hey, start minimization. So I changed it to UFF potential. We go a little bit here. And then I say, okay, optimize it. And here you are seeing some things are happening. There is auto opt, the energy is changing, and the change in energy is also changing. And we put some limits here. We say that when the change in energy, so with every step, when you update the coordinates, you see the coordinates are changed. Now you don't see any change because there is very small change. It's not perceptible. Then with every change, the energy will also change. And if the change in energy is, it says 0, but it's essentially practically you can never achieve 0. It would be 10 to the power minus 8, 10 to the power minus 9, whatever kind of cutoff that you say. You can say my 0 is, if it's below 10 to the power minus 7, that's where my 0 is. So you can set it like that. Then you see that, okay, I have an optimized geometry. You can also put more sort of constraints on it. You can say that it's not just the change in energy. I also want to evaluate what is the total force on each of the moiety, and the force also has to converge. Or you can also come up with, like, many, sometimes in optimizers you have 4 or 5 different conditions which have to converge. But I want to give you an intuitive feel of what it means to optimize the geometry. And we will follow one simple algorithm, and I'll also show you an interactive as an interactive visualization, because with force fields, it's easier to imagine in your head what's going on. When you go into the quantum mechanical part, it's essentially the same, except the description of potential becomes much more complex. And I'll try to do my best to give you a good intuition there as well. So what happens is, let's say your system, this is the state of the system W. It's called cost, but in optimization, we call it a cost function that has to be minimized. But essentially, this is essentially like your potential energy surface, your total potential energy. Let's say your system is here. Then you want to know where to move the system. Now imagine that you are in a dark room. You're on a road outside in a village. The road is not very flat. It's like, in the countryside, in the forest or something. You want to know how and where to move in the dark. What you try to do, you try to feel it with your leg, like how the road moves. What kind of curvature do I have? Am I going to fall? Is it flat or is there a curve? What you are essentially doing there is you are trying to make a derivative of the surface that your leg is in contact with. You are trying to see what kind of direction I can go to, how the curvature changes. This is exactly what the system also does. You say that, okay, I touch the curve here. This is the kind, if I'm here, this is the direction. If I move here, the direction will change, right? This is the whole concept of a tangent on a curve, that it gives you the direction. You take the first derivative, it gives you the direction, and then you update the atoms slightly. And you try to see if the energy is decreasing or increasing. And if you move it along the negative gradient of the energy, you will see. So if you move, this is the gradient, right? If you try to move, you will see that the energy keeps on decreasing. If the energy increases too much, if you go from here to here, you see, oh, I am past the minima, the sign of derivative have changed. Then you try to bring back the system. So you do a lot of back and forth, and eventually you want the derivative of the energy to be 0. And you can also do a second derivative to ascertain that you are at a minimum. But this is how optimization works. What you do is you change the nuclear positions, you update it. You essentially update the nuclear positions. That changes the potential that your rest of the system is experiencing, because potential is dependent on what? It is dependent on, essentially, if you look at all the terms, they are essentially dependent on distance. There is some kind of dependence on distance. Even the angle, you can think of it as like sort of a coordinate. They are dependent on internal coordinates of the system. You can model it as a distance, but essentially an angle, so sort of a bend. But you can think about it's dependent on what kind of separation or connectivity, or like essentially R1 to, or the distance between two moieties that you have. So once you change that, your potential also changes. You get a new energy. If the energy reduces, you say, this is a good direction. I'll keep reducing it until I see that my system has arrived at the minimum. Now, to give you an intuition, here's a small it opens now here. So this is a very, this is not really based on quantum mechanics or a huge force field. This is a very basic optimization of a water molecule to show how the optimization process works. You might have seen it in your, I don't know, partial differential equation or some kind of numerical optimization courses. If not, great, you see it now. But just to give you an intuition, this is a water molecule that is distorted. So we have opened the angle a bit, and we have said that, okay, the equilibrium geometry is when it goes between these two dotted lines. This is where the equilibrium geometry would be. So what we do now is we say, okay, go via steep. There are two different algorithms, steepest descent and conjugate gradient. I don't want to get into the details of the algorithm at all, but let's play one of them. So you see what it's trying to do. It's moving the, so there is only one coordinate. I said fix the bond length, only move the angle. It's closing the angle. And as it closes the angle for 150 degrees to towards the minimum, you see the overall size of the, so if I reset and play it again, you see there is a tangent. This is the sort of the description of the tangent or direction that you have, and slowly it will reduce and it will become zero. So you see the gradient, it keeps reducing, 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 and it will eventually become zero. Energy will also become zero. Well, ideally the energy should have been non-zero if the gradient is still there, but it's essentially the change in energy that becomes very small. And you see the energy also converges. So this is how, this is a sort of an intuition of how a optimization geometry optimization algorithm works. This is also what happened when we optimized that iron complex in Avogadro. Is this clear to everyone? Are there any questions at this point? I don't hear anything, which means there are no questions. Everything is clear. Then we can move ahead. So let me share my screen again. Okay. If you have a question, just feel free to raise your hand. If not, and if I accidentally lowered your hand, just let me know. Pallavi, you have a question. Yeah, please ask your question.
Sir, in that force field, you just choose UFF, right?
Yeah.
And while you scroll down, there are a lot of other options are there. So
Yes.
I'm not getting how you choose that UFF.
That's a
Sorry.
very good question. That's a very good question. Let me address that. Let me also see if people are trying to get in. Okay. So let's go back to the, maybe I can start Avogadro and share it. Close this. Okay, here you see a CH2 moiety, where also I did some optimization. Let me edit it. Shouldn't have done that. Let's add a hydrogen to it. Stop the optimization. Let me address your question. Okay, so what I want to do is to add a hydrogen moiety. So this now becomes a methane. So you are asking, there are lots of other options, and how did I choose? Why did I choose UFF? So if you remember the UFF paper, which we will again go back to, if you remember the UFF paper, they complained about, so these are different kinds of potential. So if you go to GH chemical or they all have parameters. So these are different kinds of force fields that are available. UFF is the universal force field, which means it works for all kinds of atoms and moieties. If you remember the previous one, so for example, if I do maybe GAFF here, let's see what kind of structure it gives you. Somehow it's freezing a little bit because of sharing on Teams. Let's stop this. And if you look at the geometry, this is not the geometry of methane, right? This you can be very sure that this is not the geometry of methane. Methane is like tetrahedral.
Tetrahedral.
Yeah. If you change it to UFF now, it changes the geometry slightly, and you get a tetrahedral kind of geometry. It's freezing a little bit, so I cannot show you very well. But so essentially, what happens is that UFF has been parameterized in such a manner that it works for. It's a general force field, so it works very well for different kinds of atoms. And that's why I chose UFF, but you are free to choose any other method. You can also choose, for example, if you have DFT set up here somehow, you can also use that. Okay, I hope that answers your question. Let's get back to the paper so that we can conclude. So I showed you some idea of how optimization works. How do we encode potentials? What kind of different potentials that we have? How does torsion work? Pallavi, do you still have a question, or can I lower your hand?
Yeah, I got it.
Yeah, okay. I'll lower your
One
hand.
more, sorry.
Yeah. Yeah, sure, yeah.
Actually, but other options like we can use any sort of atoms like protein also and other also in that case. If
Yes.
amino acid structure is also okay with that UFF.
You can use
Or
any
is there
kind
any?
of you can use any kind of structure with it. UFF will fail for certain cases. There are certain limitations that you might encounter, if, especially if there are non-trivial kind of bonds. When you have lots of weak interaction and then things are oriented in a slightly that does not go by the kind of chemical encoding that it has, then it might fail in certain cases. But most of the time, it gives you very good geometries. It gives you a very good starting point. In fact, UFF is one of the most recommended methods to clean up the geometries that you work with.
Okay. So is there any characterization like we have for this force field, like different types of force field? If you want to study more about it, it has any characterizations
Yeah, I think
like different.
yeah, I think you can look into review papers. Maybe it's a good
Okay.
point. Let me note it down, and I will send you some reviews to all of you. Review of force fields, because this whole thing of force field is really large. Because also when you are, so I was recently consulting for a chemical company. They want to make some carbon negative materials. And they're operating a plant, chemical plant for that. And what they wanted to understand is that they were using some earth abundant mineral for as a feedstock, and they were reacting it with carbon dioxide, and there are lots of impurities in the system. So there were many metals that were undesirable, and they wanted to know if they can change the feedstock, if they can change the additive, and if we could have like sort of a reactor, a computational reactor, where you can put everything in a box, run a fast simulation, and get idea of how things are going to do. And these kind of problems, and give them a timeline of what it would take, what it would mean to do work with this kind of system. Because this whole thing of force field is still a very active and very big field for example, this this feedstock modeling for chemical plants, but also for battery simulations, for any kind of coarse grained application, for electrolyzers. Because with quantum mechanics, you cannot really simulate very large systems. So what you do, you make a small system, you make quantum mechanical calculation, you see how things are behaving. You essentially get dissociation curves that are described by this Morse potential or something. You try to see what kind of dissociation behavior you are getting, and then you build a force field and you fit your parameters such that it's able to capture the physics at a certain level of accuracy, which quantum mechanics decide. And then it's highly trained to make predictions on that system. So there are, when you are working with a new system, you might have to develop the force field yourself, and that's a very huge field. And it's also not easy or trivial to do. But if once you do that, there can even be commercial potential. So if you come up with a force field that works very well with, this liquid solid liquid interfaces or liquid phase modeling of multi-component systems, you can even commercialize it. There's huge potential in that. So yeah, it really depends on the system that you are working with. Okay. Thank you for your question. To essentially finish up this paper, they also describe the van der Waals interaction. They describe it as a 12-6 potential. You see, this is a negative term, which means it's an attractive part, which actually appears as the, it's kind of similar to Morse potential, which is essentially the right side arm, which decays slowly. And then if it comes very close together, then there is 1/12 potential, which really repels things apart. And that's why you get an equilibrium. And they try to also include some concepts like, ionization potential. They know that the wave function essentially has some approximate relation with the ionization potential. So they also make use of those kind of relations to build a force field that eventually can predict some experimental parameters of interest. So they really do a lot of mathematical playing here and there to, exactly tailor the terms that are there to make some predictions. And if you look at, for example, optimized Lena-Jones parameters that they have the experimental values and they try to make very good fit. And you can see that it's actually a very decent fit that they have made. And finally, they also make predictions of geometry. So you see, these are some hydrocarbons and they have made predictions of the bond lengths that are there. And they also show you what the experimental bond lengths are. So this UFF method, then they validate on a certain benchmark where you have experimental data and show that it works very well. Even for these complicated systems, it works very well. And I have actually used it in my workflows before. And I can tell you that it's a very good starting point, especially if you use it by making certain constraints, which is something that I will try to cover in the next lecture. So this paper is, I will not dwell more on this paper. An interesting thing that I wanted to show you that immediately after their paper, they have yet another paper in the same journal, same issue probably, where they also apply it to organic molecules. That was kind of funny. But I hope this paper gives you some idea of what goes inside a force field, how do you build it, what kind of things that you need to look into, and how do you validate it. And today, there are also many databases against which you can validate if a new method that you have developed, if it is making reasonable predictions or not. There are specialized databases. So, if you're working with transition metal complexes, you have, I don't remember the exact name, but you have the PM3TM for transition metal databases, but also there are some other databases where you, for example, when GFN2-xTB method was developed, they showed it across databases for which you had, for example, you had accurate thermochemistry done or certain accurate parameters were known and try to show how much it is able to reproduce it. So that's what goes inside it. Do you have any questions about this paper? Akriti.
Um, so I wanted to ask, as you were discussing that UFF only deals with systems, so how are the surroundings involved? Say if you are doing a molecular modeling of a cellular system, then how will that come into play?
That's a very good question. So essentially, if you are doing a complex molecular dynamics simulation, let's say you have a protein and you have lots of, or you have a very large protein, like I worked earlier with acetylcholinesterase, it's an ellipsoid, and there is a 20 angstrom George that goes inside where the active site resides. And then there are all the solvent molecules. So you really have a huge system at hand. And so typically you would not necessarily do it with UFF. You'd go with more specialized force field. There are force field, the amber force field, the Gromos 96. There's a whole plethora of force fields that people work with. What you would want to do, you will first take a quantity that is known. For example, you want to maybe you want to start with geometries, or you want to start with some kind of free energy profile, or any kind of energetic or structural parameter that is known, and you'll see how that force field predicts that particular quantity of interest for your system. If that's not available, then you are in some trouble, but you always have to try to find out something that you can validate your model against, because all models are wrong. Some of them are useful. This is a famous thing in physics or modeling. Models have a certain regime of validity. So it's always good to model it to see how your system is behaving and do some sanity checks. And this is true not just for force field. This is true for any kind of computational model that even if you do DFT, you want to do CAS-SCF, you want to do ab initio molecular dynamics, you always try to validate it either against a higher level of theory, if that's available, or you try to validate it with experimental data. One thing that people often do is, if they are modeling this, solvated phase. So if you are looking at cellular components, for example, then you have lots of biological material, but you also have lots of water involved. 70% of it could very well be occupied simply by water. And you have ions, ion channels and everything involved. So what people do is they try to look at what the density of water would be. what is the experimental density of water. They try to do a plot of radial distribution function. And usually you can also find some experimental data that under such confined situation, what is the structure of water? And then you try to see, is your method reproducing the correct structure of water? Because if it does that, then your surroundings are very well modeled. And then you can also try to look maybe into acidity or basicity of certain moieties, whether the the pK is correctly being predicted or not, if that's a quantity of interest. So these are some of the different ways that you would essentially validate your method against. Does that answer your question?
Yes, sir. Thank you so much.
Thank you. Any further questions?
Sir, can you please share the link of the paper that you were showing, if
Yes,
possible?
yes. Were you able to access the? So if you go to the chat, there is a Google Drive link. Where did it go? Not this collab, but yeah. So if you go to this Google Drive.
Sorry, sir, my chat got reset because I had rejoined.
Okay. Yeah, no problem. What I will do is I will share this again. Do I copy link? Okay, that's a good point that you mentioned. The chat has been reset because then all the information is lost. Okay, great. So if you access it here, you will see that there's a paper, there's a PDF called Rape et al. 2002 or something with UFF. You can download the paper there. And if you have any troubles accessing, just let me know, and I will I can also share it directly. Yeah, perfect. Any further questions from anyone? Do you find the disk anthropic artifacts with animations, are they useful? Do they give you some kind of intuition to understand the system?
Yes, sir. They are very interactive.
Okay, perfect. You can also, I would encourage you to try them out yourself. Just go to anthropiccloude.ai and you can put a prompt of whatever you want to visualize. And if you tweak it a little bit, it gives this really beautiful visualization. You can even get some computational chemistry done out of Cloud or ChatGPT. They have gotten very good at it. In fact, when I was preparing for the quantum part, and I wanted to do it in a manner that I have to use less number of equations, or even if equations are there, they are not a blocker for you to understand things. And trust me, it's very hard when you get into the quantum regime. I did a lot of sparring with ChatGPT on how this is, how Consam had this idea, how do you explain it, and it did a good job. It makes some mistakes, but it did still did a good job. So coming back to the lecture. We learned about geometry optimization. So let's say you have now you have defined the potential, the Hamiltonian of a system. You can derive what is the minimum energy of the system. You can also do molecular dynamics simulations, which I'm not showing in details here. That could be a separate topic in itself, and also a very useful one. So you know the underlying fundamentals that are needed to do these kind of things. Now comes the frequency calculations. What do you really mean by frequency calculations? So if you take a mass and a spring, so that's the favorite of all physics. They always go to the harmonic oscillator. If you take that and you nudge, and you essentially pull the mass, it will vibrate, right? If you think in terms of energy, when you have not stretched it, when it's like at this equilibrium distance, then it's at the bottom of this minima. Put this in full mode. Okay, and get my laser pointer. Okay, so when you are here, classically the molecule is not moving. There are no vibrational modes. If you nudge it a little bit higher, right, which means you have displaced the system from its equilibrium position, then it will come back. It will oscillate. It will come back. It will essentially oscillate. In quantum mechanics, what we say is that this is not a continuous energy curve, which means there are only certain states that are allowed. In classical system, all states are allowed. You know that if you stretch a spring, it will sample all lengths. It will go, if you stretch it from 1 centimeter, 3 centimeter, it will come back from 3 to 1. It will not say that, okay, I'm not going to be at 2.5 because it's a classical system. Well, weird. Quantum mechanics can't say the same. But let's think classically that it will essentially vibrate. We can try to get the frequency of these vibrations, and they are very important. Is there a question? Advik, is your, I think they have a weaker internet connection or something. In any way, so if you are at the minimum, if you take a derivative, we saw that the derivative vanishes at the minimum. The derivative is 0, and the second derivative is positive because it's a minimum. If it were a maximum, the second derivative would be negative. That's also how you try to get the idea whether you are at a minimum or a maximum, or if it's a cusp, or if it's like a inflection point. That's what second derivative will try to help you get there. So okay, system can vibrate, which means if you take, for example, a molecule like carbon monoxide or carbon dioxide and you excite it, it will have a certain vibrational frequency that will come. If you do a spectroscopy on it, you can see it in the IR regime. It has a certain IR spectra, and CO stretching frequencies have a particular signature. In fact, that's a very useful tool uh, to study molecules that contain carbonyl groups. Like, because it also tells you what kind of electronic environment is there. How? Just with this simple picture. Just with this simple picture, you can imagine that if you start to add more energy to it. So you see this whole parabola, it depends on the value of K. If the K is very small, if it's not very large, then it will open up a little bit more. So that it will, if you nudge the system, it will vibrate a little bit slowly. It's a weak spring. It's not a very stiff spring. If it's smaller, then it's a very strong spring. That gives you an idea of what kind of intraatomic interactions are there, how strong or weak the bonds are. And that in turn gives you an idea of the chemical environment. Because if you have things that bring more electron density in the system such that the bond is activated, becomes longer, which means it will vibrate at a smaller frequency. And this is a classical way that you use in computational chemistry, but also in spectroscopy, to see what kind of chemical environment you have around, for example, a carbonyl group, but also there are other groups that appear on the IR spectra. That's why these oscillations are important to calculate. So if you have a diatomic system, just 2 atoms, then you only have to worry about a bond. If you have a nonlinear molecule, then we talk about degrees of freedom, which I skip intentionally here because it starts to get more complicated. But essentially, you can say that you can nudge the system in different ways. If you, for example, have a water molecule, you can change the OH bond, it will vibrate. There are 2 OH bonds, and then there is one angle that can change, which means there are 3 ways in which the system can vibrate. There are 3 modes of the vibration. And in reality, it will be a combination of all 3. Just like if you look at XYZ coordinates, if you say that I want to go at a certain point in space, you have all 3 parts. Like X, it's a combination of the X-axis, Y-axis, and Z-axis come together that gives you a point in space that you are. Similarly, you have the normal modes or you have the vibrational modes of the system. You combine them, and when you apply temperature, the system will vibrate. Why is it important? One thing is that we are able to get insight into the electronic structure or electronic environment of the system. But there's a little bit more to it. I will take a 5-minute break, but I will leave you with 3 questions that I want you to answer when I am back. I'll A show of hands. Who wants to? You don't necessarily have to be right. Okay, it's not that you have to be right, but who wants to take a jab at it, to make a guess if you don't know about it? If you don't respond, I'll just randomly nominate one of you. Okay. Yes, Pallavi, please.
For the frequency calculation, like as if we go deep dive into frequencies, different types of frequencies, like stretching frequencies. So in that way, we can characterize the structure of that compound with the help of stretching frequencies in spectroscopy. That's why it is important.
That's right. Do you also want to give a try on how do we get thermochemistry out of it, or but yeah, do you want to give it a try? How we can get thermochemistry, as in Gibbs free energy or enthalpy calculations out of it, which are statistical properties?
Or like we can check the randomness too out of it, like in
Yes, that's right. Actually,
yeah.
you've taken a very good direction. You can check the sort of the randomness. You can get idea of the entropy contribution, right?
entropy contribution. Yeah. And with the help of that, we can check the spontaneity, like if we want to carry forward this into some reaction.
That's
We
amazing.
can
That's a fantastic answer. Yeah, I like that. There was another show of hands that went down. I think it was either Akriti or Ayushi or Daniel who are at the top
Sir,
of my. Yeah. Yes.
sir, I wanted to answer the question of frequency calculation.
Mhm.
So, as Pallavi said already, it is important for entropy calculation and all. And I think so, frequency calculation gives an idea of reaction pathways, like through transition states, and we can get an idea of is like we calculate IRC files in a transition state, so we can get an idea of whether this reaction is going forward or not. Like, is it
Fantastic.
we get an idea of pathway.
Great. That's a great answer as well. That's very true, and that's why frequency calculations are very important. It helps you characterize um, when given a geometry, whether it's where does it sit on the potential energy surface. It gives you an idea of that. And you're very right when you do transition state calculations. So for those who don't, I think everybody has heard about transition state calculation, but essentially if you have two states that are different, that have different atomic arrangements. So if you start with a certain number of atoms that rearrange to form a, let's say, reactant and a product, they're usually an activation barrier that separates them. Otherwise, they would just interconvert among each other, right? So there is a hill, energy hill that you have to pass through. And at the top of the hill, sometimes there is a transition state. It's not always there. So for example, if you do homolytic dissociation of a dihydrogen molecule in gas phase, you will not find a transition state. It will simply separate out. But when there are competing sort of, when you have two different kind of minima, then there is like sort of competing forces that try to keep the molecule on one side or other. So there is like an intermediate structure or a transient structure where if you do frequency calculation, then along you can describe a, you said IRC, so you can describe an intrinsic reaction coordinate along which the reaction coordinate along which the reaction happens. If you take the derivative of potential energy on that part, you will see that you will find a negative, you will find an imaginary mode there or a negative frequency there because it's a double derivative. So if you are at a maximum on one side, then your double derivative is negative. I did not include a lot of that mathematics here, but yeah, feel free to ask me if you want something more about it. But yes, indeed, that really helps. To come to the question of thermochemistry, you might have read about things like enthalpy, entropy, Gibbs energy, and both Pallavi and Ayushi, they touched upon that. It gives you an idea of randomness of the system. Now, how does it do that? See, when you do statistical mechanics or thermodynamics, you never talk about a single particle in isolation. Never. I mean, you can do molecular dynamics simulation. You can say, okay, I have a box of particles, but these frequency calculations, they can be done on a single molecule and you can get all the thermodynamic property out of it. I mean, there is an approximation involved, but still. And so the question that comes out, how can you do calculations on one molecule and get statistical property out of it? That sounds a bit perplexing, but in reality, it's not if you think about what temperature means. So some like just few slides ago, I reminded you that temperature is we are talking about statistics, which means we are talking about a large number of particles in a certain kind of ensemble, in a certain kind of thermodynamic state. And that means when you say that a system or a collection of particles is at a certain temperature, there is a probabilistic distribution called the Maxwell-Boltzmann distribution, probability function of velocities that are involved, which means systems have different kinds of velocities. If you think in terms of molecular vibrations, which means if you have a potential energy surface or potential energy that looks like this, if you apply temperature, you will have molecules that will be excited along the entire range of this whole potential energy surface. There will be lots of molecules that will be close to the equilibrium. There will be slightly lesser which are far away, let's say here, and there will be very few, like maybe 1 in a million or something, that will be really at the top of the potential energy surface. If you were working with a Morse potential, you could also say that there will be some molecules that will be in a dissociated state, but we are not talking about that here. We are assuming that the temperature that we are applying is still in this region around the minimum, so that molecules are vibrating. That means if you study the vibrational modes that are there in the system, you essentially, with those vibrational modes, you can already look at what kind of vibration states the system or a collection of particles would sample in the harmonic approximation. Then you can essentially derive all the thermodynamic properties that you need, because for these thermodynamic property, you simply need what kind of energy states are accessible under the applied temperature conditions. So you essentially create the idea of the ensemble that by calculating the vibrational modes of a single molecule, and then you can get all kinds of thermodynamic properties out of it. Any questions here? Pallavi and Ayushi. Pallavi first, and then we can take Ayushi's question. Yeah.
Sir, to conclude the answer of third question, we can just directly mention that to see the kind of energy states which is like efficient for our structure. I mean, in conclusion, what we can say about it.
In conclusion, what you could say is that
in third question.
Yeah, in third question, how can the calculation of one molecule helps us get the thermodynamic properties? So thermodynamic or statistical properties belong to an ensemble of molecules. There should be, ideally, there should be like an entire collection of large number of molecules. And when you apply temperature, when they are at a certain temperature, then different molecules will be in a different vibrational state or a different energy state, which is thermally accessible. So the energy, so vibration and energy, they are essentially same side of the two coin, because the Planck's relation says that E equal to h nu. So if you have the vibrational frequency, you can assign that to an energy state. So you essentially get all the energy states that are accessible, which means you have essentially create a large number of states that the system can sample. Once you know that, you can automatically you can create a partition function, you can apply all your statistical thermodynamics and get the quantities of interest.
Okay. Yeah.
So there is something that I wanted to add. So basically, we are just tweaking these parameters, since as considered in a biological system, that one single molecule does not act in isolation. So tweaking these parameters essentially puts that entity into a direction. For example, if we consider a protein folding problem. So this is what comes in concern of these properties that we're talking about, isn't it?
Actually, protein folding problem is a little bit more complicated than that, because the protein itself is composed of, so when you place a protein in a for example, a thermal bath, there are different ways to think about. So if you look in terms of vibrational frequency modes, you can of course attach a sort of entropy to it, to a given structure. But in protein folding, we are actually talking about a dynamic system, which means you have an unfolded structure and you have a folded structure. If you want to characterize these two states separately, you need to come up with an order parameter of the system. So you can say that I have order parameter Q, which is based on what kind of overlaps I have within the system. If the order parameter is close to 1, which means all the contact points are essentially on top of each other, they are overlapping, it's a folded state. If they are like completely open, Q is 0, it means it's a completely unfolded state with high entropy. if you characterize those, and that you have to sample again, you have to essentially do an entire molecular dynamic simulation. You cannot. It will be very difficult to obtain that with frequency calculations alone, because these frequency calculations, they operate in the harmonic regime. So they essentially don't sample the entire order parameter of the system, because there is essentially a phase change from folded to unfolded. With frequency calculation, you don't make a change of the phase. You are essentially saying that given phase of the system, for a given phase of the system, what kind of energy states are here. For protein folding, you are saying I have two phases of the system. What kind of states are there? And for that, you need to also look into the dynamics of how it evolves over time and what kind of states it samples. If you get an order parameter, you can then try to say that, OK, this is thermally activated. So you can apply like some kind of a Fermi distribution or thermal population distribution of what is the distribution of the different states. And that you can transform then into write an expression of the Gibbs free energy. So there is a subtle difference there, but the overall thinking, it's the same. And I really like that you are trying to connect these two things. That's very good thinking.
Okay, thank you so much, sir.
Thank you. Any further questions from people? There's someone in the frequency. We have Roshan's frequency calculations help determine molecular vibrations, which are essentially yes, indeed true. That's really correct, and that's the essence of it, Roshan. That we try to characterize where the molecule sits on the potential energy surface, and that's essentially what we're doing. So you are indeed right in saying that. I think some people have a bit of unstable connection. Fatima?
Yes, hello, sir. Hello. So, okay, the question is like if we talk about free energy, so that it governs equilibrium, right? So, what governs non-equilibrium systems?
That's a great question. That's a great question. So, see, when we are talking about free energy, we are talking about equilibrium states. That's indeed true. When you are talking about non-equilibrium states, which means essentially you are talking about, for example, okay, this dives a little bit deeper. So you can do a lot of equilibrium, like thermodynamics or statistical mechanics. Then there is this whole thing about non-equilibrium statistical mechanics, which means you are making changes to a system where there is a certain non-zero velocity. So what I mean is, let's say you have a active site of a protein, and you have something that binds there. Ideally, if you want to do a free energy surface of how it unbinds, you want to move it infinitely slowly. I want to make a reference to maybe what you have studied in school about electric field. What is an electric field? How do we define it? We say that electric field is the force experienced by a test charge, unit charge, that is moved from infinity to to close to the point of contact, and that's the field. The force that it feels is given as the electric field, and what we say there is that we are moving the test charge infinitely slowly, which means everything is in equilibrium. So at any point of the system, the changes that we are making are reversible. When you are looking with non-equilibrium system, the changes are not reversible, which means you cannot simply take derivatives of your force and try to say that, okay, we are moving we are under equilibrium, so I can calculate the force, or I can integrate the force and get my potential energy surface out. The way to do that is that there is something called I forgot. There are two names, that the Jarzynski inequality, Jarzynski-Schwarz, or some kind of, I'm forgetting the exact name. You use that inequality in the systems to compute, to sort of extract the free energy. What it says is that, imagine that you are doing an atomic force microscopy experiment. What you do there, you take like a cantilever, you try to probe the system a little bit, and you try to get the idea of interactions. There also, the interactions that you are measuring with atomic force microscopy, you are not necessarily keeping things under equilibrium, because in reality it's never possible to make a movement. It has to be infinitely slow, right? So what you do is you try to do it multiple times. You take a statistical average, and then there is an inequality that tells you that you can get sort of an an upper bound or there is an inequality that tells you that you are able to sort of get a bound of the free energy with which you can guess what your free energy. You can never really hit the true free energy. You will always be above that, but you know that, okay, this is a good estimate of my free energy. And if you do it multiple times, like, back and forth motion, then with statistical averaging, you will reach very close to the actual free energy. So that's how you work with non-equilibrium systems. But if you're looking into molecular dynamics, simply equilibrating the system, you always want to have the system come to equilibrium. To sample non-equilibrium phenomena, you will have to choose a particular reaction coordinate, add certain kind of energies to it, and then try to do do these essentially thermodynamic tricks to derive what the actual free energy is. Does that answer your question?
Yes, sir. Yes.
I can also send you some more references. This was actually the first project that I did in computational chemistry. It was essentially about getting equilibrium work out of a non-equilibrium simulation. You can also look into steered molecular dynamics simulation. This exactly deals with this kind of problem.
Okay, sure.
Okay.
Sir.
Let's move forward then. So we touched about frequency calculations. Here are some references about some advanced force fields. I won't dwell a lot on it, but I will also send you these papers for you to read. For example, if you want to sample reactive phenomena, you can also look into ReaxFF. It's a very popular method that is used for certain systems, or empirical valence bond methods that allow you to break and form bonds. Summary. To summarize so far, we have used classical models that help us predict molecular behavior. We have looked into Hamiltonians and what kind of interactions entail the interatomic interactions in a system that describe the energy of the system. And we also know by now, we have not touched in, that quantum mechanics will provide deeper insights. I was very optimistic that I would have covered all of this in 1 hour. So this is not the time for a break. Please ignore this slide. What I actually wanted to do now is do a simple hands-on before we go into more theory. Let me close this. On the Google Drive, you will find a. So what you can do is you can either take your own molecule that you find, or on Google Drive, you will find a N2H4.xyg. Let me see if it's there. Yeah, it's there on Google Drive. Just download it. Go to the Streamlit app. I think all of you have a link to it. If not, I'll also put it in the chat. So this is essentially an app, a small app that I made, with which you can run some calculations, and we'll look into what kind of thermodynamic properties are predicted. Maybe I'll do it together with you guys. So I'll also open a screen. Let me share my screen. Yeah. Can you see my screen now?
Yes, sir.
Yeah, great. Tell me something. Is there someone who has not used this app because you received the message too late? I also sent it very late, that you are not familiar with what this web app does. Everybody knows about it. That makes me very happy. Okay, in any case, what I'll do is I'll demonstrate what this really means and what it is about. So don't get confused if something seems like, oh my God, what's going on? So what this app does is it uses a method, a quantum mechanical method, which is, it's not a force field. It's a semi-empirical method. I have not touched this and I'll not be touching the mathematics of it because it will confuse you more. But just think about it like this. It's a quantum mechanical method with which you can do geometry optimization, frequency calculation, a lot of other stuff, and it goes very fast. That's why I can host it on a free cloud app. And it's not very accurate in the sense you cannot do all production grade calculations for a complicated system, but it's a very good first start. It's slower than UFF, but it's still fast enough. So what I have done now is I have uploaded a XYZ coordinate. You can also, if you have opened it, you can also just do alongside me. And the moment you upload it, it gives you the the atomic coordinates. So you have nitrogen is an N2H4 molecule, and it also lets you visualize the molecule, right? So you can see the molecule here. You can also say, if I want to see atom indices, there looks a little bit ugly, but yeah. And you can also see what the labels are, like what is the atomic symbol. Then we come into the reaction parameters, calculation parameters. What we want to do is we want to optimize it, but we also want to do frequency calculation. Frequency calculation is also called a Hessian calculation. So we do OHS. It will optimize the system and then it will do a Hessian calculation on it. Charge is 0. It's what's it called? N2H4. Okay, I'm suddenly forgetting the name, but if you remember it, please tell me. Charge is 0. It does not have unpaired electrons. We also don't choose any solvent model here. So it already constructs the command for you. It's XTB input.xyg minus OS minus charge minus my charge 0. You can also run this if you have XTB installed locally. You can also run this on your own system. But I will run it here. So it's a run calculation. It's already done because it's a very small molecule. Here you can see the calculation output, but because I have the admin console, I can also look at the terminal here. So it says that, okay, the calculation is complete. Warning errors, no, it's normal termination, and you can download all the results. I'm not going to download the results. I'll show you the optimized structure. It's not very different from the input because I was already using a good geometry, and this geometry input was actually optimized at UFF level. So you can see that UFF gives you good. Actually, maybe it was pre-optimized also at XTB level because this has no. Yeah, there are no parameters in the trajectory. It's already optimized very well. Okay, let me show you something that I wanted to show you. So if you look in the output file, in your case, because okay, if I take this, you might get confused. If you download output.out file, so maybe I'll download it here. Okay, and I will not open it because I suggest that you open it. I'll do it here in the console. If you open it and if you go inside it, it's a big file. Keep scrolling, you will find that it gives you the total energy of the system. Right? It essentially evaluates what the energy is in the which is where the minimum energy comes out of the system. And it also gives you lots of parameters. It gives you all the distances. Oh, hang on. This cannot be true. Maybe it's looking at some other. Oh, okay. This console probably did not update. So let me then open the output.out file because it's a different thing. So can you see my terminal here?
Yes.
Right. So I'll go to output.out and make it a little bit bigger, but not full screen because. So what I want to show you is how frequency calculation is used to determine the thermochemical parameters, the thermochemistry. And this is a good example to show it. I mean, you can also, I think you might be able to do it at UFF, but I have not done lots of frequency calculation with UFF and I don't have a software that can immediately do it. This is easier. And so I will just use this. There are lots of things that it does. Maybe I can walk you through it. So it has lots of references. If you use it, cite it. It gives you the calculation setup that you did. And then it says that in the beginning of the system, what kind of interactions it has. So it says some kind of Hamiltonian related parameter. This is important. This tells you what is the dispersion interaction. So you remember the Lennard-Jones potential. This is an equivalent of that. It's a little bit more complicated, but it has 4 parameters: S8, S9, A1, A2, and it gives you those parameters with which it essentially predicts what is the dispersion, what is the weak interaction in the system. Then it also computes the repulsion energy that is there. So there's the there are different components to it, and then there are certain other order because it essentially calculates the Coulomb interaction in the system with using a certain kind of model. So it gives you lots of different parameters, and then it has certain basis functions which we have not touched into. It says I will do 250 maximum iterations. The system has 14 electrons. It has 8 cells, blah, blah, blah. It has no, we are not using any solvation. It's not a restarted calculation. There is no constraining potential. I think that's what PC potential means. I'm not very sure. It also uses electronic temperature because of the certain, you can ignore this term for now. And then it does essentially calculation. It calculates the energy. So it gets the energy, it looks at the change in energy, and you see that finally the change in energy becomes very small. It becomes smaller than 10 to the power minus 9. It also looks at certain RMS values and what's the gap and some other parameters and says that, okay, the energy of the system has converged for this. And then the energy has converged. Ideally, if there were multiple steps involved, it would again displace the coordinates a little bit and do the geometry optimization. So it gives you the total energy, it gives you HOMO-LUMO gap and everything. What I want to show you is, so it has done the optimization, cycle 1 done, final structure is here. It gives you the equilibrium bond distances. It also does one more single point calculation to get the energy. And then I want to show you where it does the frequency calculation. So here is the frequency printout. See, it has 6 eigenvalues that are negative. These are essentially this essentially relates to translation and rotational degrees of freedom that the system has. They are always negative. They should be negative, because if you take a molecule and put it, displace the entire molecule, that's not going to make any kind of change in the molecule. It's still the same molecule. So it's like, it's an invariant transformation of the molecules. That's why you will always have, some software might even suppress these printouts, but you will always have these modes. Let's admit this person. Okay. Then it gives you eigenvalues of the frequencies. I don't have a right away setup to visualize the frequencies today for you, but I'll do it in the next class where we will do a little bit things in more detail. But these essentially are the different vibrational modes in the system. Some of them correspond to NH stretching, some of them are NN stretching. You can even look at it here that maybe these probably correspond to like some of the bigger ones. And then you have like, equivalent 4 nitrogen-hydrogen bonds. So these 4 probably correspond to your nitrogen-hydrogen stretching. And then it computes, so it also gives reduced masses, blah, blah, with the help of your frequency. So it said, okay, I have 12 frequencies. There are no imaginary frequencies. So it's a stable structure. And then here it computes the partition function. Partition function is something that you can compute when you do statistical thermodynamics. You look at the energy states that the system has, and depending on the kind of ensemble you are using, you calculate a function, and then you essentially use statistical mechanics, the formalism, to compute enthalpy, heat capacity, and entropy. So this is what we were discussing about, how frequency calculation comes into calculation of this property. It also gives you like, what's the essentially the H0 and like at a certain temperature, what's the difference in enthalpy, what's the PV correction. And with all of this, and there is a very nice PDF on Gaussian, the Gaussian software about thermochemistry in Gaussian. I'll share a link of it, or I'll just upload the PDF for you. Read about it. It goes into details of how frequencies are used to actually get the quantity of interest. And if you have some background in bit of statistical mechanics, you will be able to follow it. So it gives you the total free energy. So remember, we started with electronic energy. Electronic energy corresponds to one molecule. And then we did the frequency calculation. So you have entire ensemble of energies of states that come into it. With that, you are able to do statistics, and then you are able to derive thermochemical properties. And once you have this, you will also be able to look into what is the delta H or delta G of a chemical reaction. Because what you will do is you will compute it for reactants, you will compute it for products, and then you can look at what's the change in the entire energy. So that's why this is very important. You can also look at what is the activation energy barrier if you compute the transition state energy. This is what I wanted to show you. I'll close this now. Were some of you also able to run this on your own?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Good to know that. Question for you guys is, are you comfortable with using a terminal?
Yes, sir.
Is there someone who has not used who is not comfortable or has not used the terminal? It's okay. It's not a problem. Okay, seems like everybody has used it, but in case you are not very comfortable, don't let that be a blocker for you. We will always come up with tools and techniques that can help you. That being said, it's important to also learn about using a terminal, get proficient with it, Also look into bash scripting, how you can write small script to parse files to get quantities of interest. And also consider, if you haven't done so already, also consider getting simple tools like Notepad++. They give you lots of functionalities that a command line will give you, but it's a graphical user interface that helps you. And then there are other, I think Emacs and some other editors are also there that help you. So don't let that be a blocker. If you are using a Windows system, I use the Windows system throughout my PhD and postdoc, but I always had some kind of Linux system available, either as a Windows subsystem of Linux, or because we always had HPC centers where Linux environment was there, or we made a partition in the grub and had both dual boot systems available. Try to get more and more familiarity with Linux. Also try to get more familiarity with what cloud computing is, how things work on HPC. There are lots of free resources these days available to get you up to speed, but we can talk about it a little bit later. Are there any questions at this stage about frequency calculations or anything? Or anything at all that we have touched? Feel free to ask questions, and this is your chance to ask questions. Are you able to follow? Is there something that is difficult? If not, I'm going to ask you to turn on your camera so that we can make a nice group picture, and then you can turn it back off again to save on the bandwidth. I don't see any cameras turning on. Do you want me to make pictures with just the icons? Okay, thank you. I think half of the people probably went asleep or something. Don't be shy, huh?
So can you say if you can allow me to access the camera? I'm not able to do it.
Oh. I don't really know. I think it's a setting on your device, because here I see I can only mute or unmute people or pin people, but I cannot. I don't think you can turn camera on or off for people. But if you cannot do it, I can understand it. That's all right. Others, are you planning to? Oh, okay. Nice. Okay. So we did not. So Teams by default does not place everyone who has a camera on the first screen. So what I'm going to do is I'm going to make 3 screenshots. So get your best smile out and say cheese, or if you are want to say it in Dutch, you say kaas. One picture done. We do one more. And this time, instead of cheese, we can say paneer. And one more with all you fantastic people. Smile. Okay, we have made some nice pictures. Thank you for your cooperation. Yeah, and feel free to turn it off, because I know in a large call it affects the bandwidth. I will show my pretty face, no worries, so that you can follow along. Okay, share my screen back. Do you guys need a short break before we go into the quantum aspects of it? We can take a 10-minute break. We start at 4 p.m. Is that okay?
Yes, sir.